So let's get started, everyone. So it's a great pleasure today to have Stephan Mandt, who's coming from UC Irvine. Stephan has been doing a lot of very interesting work, especially on lower latent spaces and data compression, latent variables, autoencoder, and whatnot. He's coming, he has background in physics, theoretical physics. So he actually got his PhD in theoretical physics, not computer science. And then moved on, he actually did a postdoc. He was working with David Bly, was Princeton at the time, then Columbia. So that's how he started getting into machine learning. So he really has his roots into physics and machine learning together. So that's really great and makes a lot of the communication, with the physical scientists much easier in a sense. Then he actually worked for Disney, so a very interesting experience. And then he's been at UC Irvine since then, assistant professor and then now associate professor. And he's been very much at the forefront of some of the collaborations with the climate scientists. So last week, we actually had Mike Pritchard. They've been together working on a lot of very interesting problems and how we can use some of those tools that we can use for some other processes, such as natural language processing and whatnot, to actually the natural science and the physical science. So very much looking forward to your talk. Thanks for being here.
Thank you so much, Pierre. It's a great pleasure to be back. So I actually lived here in Columbia campus for 2 years. So it's always feels a little bit like home to be here. So title of my talk is Deep Latent Variable Models from Data Compression to Natural Science. And what I would like to argue here to start off with is that deep latent variable models are in some sense, or in particular latent variable models, are one of the most successful concepts in machine learning. So what is a latent variable model? So, oftentimes one associates this with this kind of picture of an iceberg where sort of only 10% is observed, and the vast majority of it is sort of latent structure that you cannot immediately observe. But we know it must be there because otherwise we'd have like a hard time explaining that floating mountain, right? So the message here is that, if we assume the presence of unobserved variables, it sort of makes our modeling assumptions much easier, because otherwise we'd have to kind of work with very obscure, complex models of our world. So this has been a surprisingly robust concept over many decades of machine learning research. So we started off with, many decades ago with simple mixture models. Then about 20 years ago, David Bly brought forward these topic models, which have become very popular in NLP. 10 years ago or so, we were really excited about the advent of variational autoencoders that generate structures, for example, structured objects like handwritten digits. And then most recently, we're all amazed by the huge successes of diffusion-based models that are much better in terms of generating perceptual appearance of humans. So those are now better than GANs. And the point I want to make here is, again, while inference algorithms and paradigms have constantly changed over all of these years, for some reason, this idea of a latent variable has been always there. So as I said, I want to focus on two application areas that got comparatively little attention. And this is, on the one hand side, compression, on the other hand, natural science. At first, they seem sort of unrelated, but hopefully we'll kind of learn to embrace certain connections later in this talk. On the one hand side, I want to talk about the climate science collaboration that Pierre brought forward and mentioned earlier. And I also want to talk about both applied projects and theoretical projects in this new recent area of neural data compression. And that, I want to argue, has very elegant, research aspects to it, right? On the one hand side, you can go very theoretical and almost solve information theoretical questions. And on the very applied side, you can really try to compress your data. And who knows, maybe there are some applications for compressing climate data and Earth system science data. All right, let's try to combine these two areas. So since this here is a climate science audience, I want to start with latent variable modeling for climate science first and motivate this a little bit. So what we've been working on is a focus on so-called storm resolving models, which are, as you all know, climate models that resolve physical processes at unprecedented length scales and kind of relatively small grid sizes. Without going too much into detail, we looked at a certain data set that was collected in the so-called Diamond project that you see on the left-hand side. So all of those here are snapshots of the Earth with subtle differences in the clouds, as you see here. They all come from 9 different climate models. So you can now simply download this data set. And they all differ in terms of how they represent turbulence, how they parameterize subgrid processes. So lots of model differences. And the implications of these differences are not very well understood. right? So in some sense, there's a lack of tools or even methodologies that would allow you to sort of compare the consequences of these different model choices on a global level. So this is the problem we would like to address here in today's talk. And of course, this is a much more generic problem in science. You can think of other kinds of simulators, maybe in astrophysics, maybe in sort of molecule synthesis, right? So this is a fairly generic problem. So this is how the data looks like. Those are these sort of 9 different snapshots, or kind of, you see videos of coming from these different models. So this is a 3x3 matrix where every entry comes from a different climate model. And what is shown here is basically on the y-axis, this is like altitude. The x-axis is a one-dimensional projection of the Earth. So this is just one-dimensional space dimension. And then what we see here are vertical velocities, in other words, wind velocities going upwards or downwards through the atmosphere. When something is red, I believe it's going up, green is going down, maybe blue is going down, maybe the other way around. But the point that I want to make here is that just by staring at the data, it's virtually impossible to sort of intercompare these different models. Right? I mean, maybe if you have an amazing memory and you're super smart, you could spot differences. So maybe I can see that those two look a little bit different from the rest, but I wouldn't be able to tell any difference between the 6 models, for example, at the bottom, and maybe also that, right? And of course, here's where machine learning comes into play. So what we would like to do is we would like to understand model discrepancies in terms of distribution shifts of the data that these models produce. And then we want to apply machine learning in order to quantify these differences between these simulated data sets. And of course, when we assess distribution differences, then one particular type of discrepancy measurement comes into play. This is the KL divergence. KL between A and 2 distributions, P, A, and B, is shown here on the right-hand side by this formula. So this is sort of a distance measure. It's not strictly a distance measure because it doesn't satisfy the triangle inequality, but it's basically a measure of distance between distributions still. So in other words, when 2 distributions are very close to each other, the KL is small. If they're further away from each other, then the KL divergence grows. And so we want to use that, or maybe a symmetrized version of KL divergence to assess distribution shifts and differences. And interestingly, there's this connection to compression. Namely, it turns out that the KL divergence measures the number of access bits that you waste when you use a compression algorithm that is actually suboptimal on your data set. Namely, when you compress a data set that comes from a distribution A, but you use a code that was optimized towards a distribution B, right? And so the penalty or the suboptimality that you incur is exactly measured by the KL divergence. So this is kind of a nice moment to switch topics and tell you a little bit more about compression. And I want to kind of cover really some very basics here on how a lossless compression and then later on lossy compression works. So the basis of lossless compression is oftentimes that we assume data are living in a discrete space, for example, on a grid. So here is a 2-dimensional grid, and the points of that grid could be our data points that we would like to compress. And importantly, the first thing we need is a probability model of the data, because we want to essentially encode data that are very frequent under that model by short bit strings, and data that occur more rarely by longer bit strings. And ideally, we would like to do this in such a way that the code length is given by the negative log probability under this probability model. Right? So if you have that, then you can actually, there are so-called coding schemes. So think of Huffman coding that uniquely allow you to convert these symbols and log probabilities into binary bit strings, and this is completely lossless. So you can go back and forth. Okay. So lossy compression, typically we are encountering a lossy, in other words, irreversible step where we lose information. And the reason is oftentimes that the data is not living on a grid or not discrete, but for example, continuous. So think about images with continuous intensity values. And then oftentimes this lossy step is associated with some form of quantization. So for example, you can think about the images as points now in this 2D space. We quantize them to an integer grid. And you also see that there's, the plot suggests that there's also a continuous probability density that we also quantize that then becomes a probability distribution over the grid points. Yeah. Now, in practice, we don't quantize in the original space. So for example, we don't quantize in the original pixel space, but what we oftentimes do is called transform coding. And in transform coding, we have a mapping from the data space into another space in which we quantize and losslessly compress. And then if we want to reconstruct our data, we then take another mapping G that takes us back from that compression space into our data space. We oftentimes like to call the data X, right? Z here is called our latent space. This is where we perform the quantization of the compression. And with X hat, we oftentimes then denote the reconstructed data. We also need a measure of reconstruction quality. So this could be, for example, a mean squared error. And that in general, we want to call a distortion rho that depends on X and X hat. Now, just by looking at this looks pretty much like an autoencoder, right? So you go from X to Z and back to X. In particular, it looks like a variational autoencoder because variational autoencoders have this nice property that there's a density model in the latent space, which is your prior, right? And so this is exactly the connection. We'll use the prior of our variational autoencoder as our probability model in which we do the lossless compression after we encoded our data into this latent space. Now, there's been a lot of thinking about how do we actually now learn these compression models in an end-to-end fashion, right? And this is kind of the big question. Can we learn these encoder and decoder transformations? And can we also learn these priors, these entropy models, end-to-end from data? If you think about it, this would be the objective function. And I apologize, this is going to be a little bit more technical. It's going to be later on, a little bit less technical later on. But this is the objective function that we would like to minimize and learn compression. On the one hand side, we have a expected distortion, right? The distortion between the data X and the encoded, quantized, and decoded data, right? So this should be as small as possible. And now we have a weighted combination between this distortion, but at the same time, we want the rate to be small, the code length to be small. And the code length, as I said earlier, is the negative log probability of our quantized encodings. Right? So depending on how we weigh these different terms with respect to each other, this is like the objective that we would like to minimize. And in particular, we want to minimize this over encoders F, decoders G, and density models P. Now, it turns out that there are various complications with that. The first one is that there's this quantization involved, rounding, in other words, to an integer grid. And rounding is not a differentiable operation. You cannot backpropagate gradients through your rounding operation. The other problem is that the probability distribution P of Z hat is actually a distribution over a discrete space. And you want to differentiate that with respect to its input, and that's also not differentiable. Now, there's been a trick to get around this, which has been very popular. And the idea is to replace rounding at training time by adding uniform noise. And the idea is that the residual between the image and the rounded image, or the quantized image, that residual, that difference, roughly follows a uniform distribution. Right? So if you inject that uniform noise into your objective during training, you could kind of argue that this simulates the rounding operation at training time. And that turns out to be differentiable. The other thing is that if we want to have a discrete probability distribution, you can actually learn a continuous probability density, which you can then do. And then you obtain actually a probability over the grid points simply by integration. Right? So this is also the other problematic solution to the other problem that we incurred. Now, if you combine both ideas and write down the new objective function that you then learn by gradient descent, you get this object. And for those of you who are familiar with variational autoencoders, you will immediately see that this is exactly the loss function, the negative evidence law bound of a variational autoencoder. When you do the following mental translations, first of all, as I said earlier, your entropy model is your prior, P of Z, right? That's the distribution for lossless compression. Your decoder is your likelihood model. And this is actually, that has to be chosen in such a way that the distortion corresponds roughly to the negative log probability. So in other words, if you care about mean squared error distortion, then your model should be a Gaussian, because negative log of a Gaussian is a quadratic. If you care about mean absolute error, then your model should be a Laplace distribution. And finally, the encoder is actually your inference model, is a box-shaped distribution. Your variational distribution Q of Z given X is sort of a uniform distribution centered around a mean prediction that corresponds to your encoder. Now, for me and others, this was very exciting a few years back. And since then, I've been fairly active on this because before 2018, I was working primarily on variational inference. And then when I learned about these close correspondences, I could really see I could now use my variational inference expertise. And my hope was to really kind of boost the compression performance by essentially applying advanced variational inference tricks to this problem of learned data compression. So if you're interested in that, there's a tutorial of NeurIPS tutorial, and there's also a review article that you could read. So one paper that we wrote, which has been fairly practically relevant, was that of improving inference for neural compression. And there we identified several suboptimalities that you can actually improve when you train variational autoencoders. The first one is called the amortization gap. The amortization gap tells you that if you train a variational autoencoder with an encoder network, this is essentially a way of doing amortized inference. So in other words, the inference is shared across all sorts of different data points. Where in reality, every data point should have its own independent posterior. You could sort of tune every new data point's own mean and variance if you work with Gaussian posteriors. And the suboptimality that you incur is called the amortization gap, and you can actually close that amortization gap by doing inference at test time. So you kind of do gradient-based optimization for every new data point that you incur and learn essentially a more compressed representation in a trained model for that new data point that you would like to compress. The other suboptimality is called the discretization gap. And this basically comes from the fact that noise injection at training and rounding at test time is not the same thing, right? And so you're not really optimizing your model for the task that you use the model for. And the suboptimality is called the discretization gap. And this can be closed by essentially at inference time, when you encode data, that you don't just follow your inference network and round to the nearest grid point. Instead, you do this only as an initialization, but then you do a discrete search on that integer grid until you find a more compressed representation. Right? This can be done by a trick called Gumbel softmax annealing that we proposed. And here you kind of see a sketch that you initialize at a certain grid point, and then you do like a follow an annealing path until you finally find a different grid point that sort of leads to a better trade-off between rate and distortion. The last suboptimality is a little bit too technical to explain. It's called the marginalization gap. This has something to do with lossy bit spec coding. It's actually something that Rich also worked on a long time ago. And yeah, this relates to inference in hierarchical VAEs, but if you're interested in that, I refer to the paper. So how well does this work in practice? So here, what you look at is a so-called rate savings plot. The y-axis are the relative savings in bit rate, so the relative reductions in file size compared to a baseline model. And that baseline model in this case is BPG, which is one of the best performing classical codecs. So its own rate savings are at 0, right? Its improvement over itself are 0. On the x-axis, we see PSNR, which is a measure of image quality. In other words, how close are these reconstructed images to their original form. Now, what we did is we took a very popular neural network-based compression model, which is the Brown curve. You see, originally, it's roughly on par with the best performing classical codec. And then we applied our two tricks, namely amortized iterative inference and this Gumbel softmax annealing trick to find discrete representations on it without taking doing it only at test time, not changing the trained model at all. And this actually led to improvement of rate savings by about 15 to 20%. Right? Which is actually pretty enormous if you think about it, right? You don't do anything to the model, you only kind of invest a little bit more time at encoding time to find a more compressed representation. You can actually also see it qualitatively on the right-hand side, but let's actually skip about that. Now, let's step back for a moment and think about where this field of neural compression currently is as of 2023. And the disappointing news, or slightly scary news, is if you look at these different rate distortion curves that have been proposed by different people, and in this case, I'm plotting quality against rate. So we want to be at high quality and at low rate. So we want to be in the top left corner. So higher is better. What you see here is actually there's been a lot of activity in the field, but you see sort of saturating gains. Right? It's become less and less easy to outperform the state of the art. And if you just look at this, you might wonder, is there maybe a fundamental limit beyond we cannot go anymore, right? Is there something that prevents us from pushing this curve further and further? And unfortunately, yes, the answer is true. There is such a quantity, and it's called the information rate distortion function. So let's talk a little bit about that information rate distortion function. So the rate distortion function the information rate distortion function, turns out to be a property that only characterizes your data set. So it's completely independent of any practical compression algorithm. And you can think of it as sort of as a quantity that measures the lossy compressibility of your data set. So in some sense, it generalizes entropy, which is sort of giving you the limit of how well you can compress your data set losslessly if it's discrete. And the generalization is the rate distortion function. It tells you sort of, given a certain level of distortion tolerance, how much can I compactify that data set. It's also the best achievable bit rate that any code can achieve. And it has a mathematical definition that I'm writing down here, but I'm basically only showing it to you to scare you, because the point is that I want to make is that this is a really nasty object to optimize, and it's basically always impossible to compute it. Okay. Before we go too much into details, let's see of what it actually does. So if I look at the diagram of all possible rates and distortions, you can think of it as almost as a classification boundary that tells us, you know, everything above the rate distortion function is something I can achieve. So I can achieve this combination of rate and distortion. But for example, I cannot achieve this pair of low rate and low distortion simultaneously. And this is very useful for codec designers, because if you're already very close to the rate distortion function, you know, basically you've already reached optimality, and it makes no sense to try to improve your codec development further. And that's why we're very excited about this quantity. Now, the problem is that this has no analytical form except for very simple Gaussian cases. And so it's very hard to compute. And so because it's so difficult to compute, we do something slightly different. As opposed to estimating it directly, we actually apply variational inference to derive upper and lower bounds to that information rate distortion function. And the tighter these sandwich bounds are, the better it is, of course, because the upper bound tells us it's a possibility result. So I know for sure that I should be able to reach this point on the curve. But also the lower bound is useful because everything below the lower bound is definitely not achievable. Right? So in some sense, we're interested in both quantities. Okay, so just very quickly, how do we get these upper and lower bounds? One result that we found is that it turns out any so-called beta variational autoencoders, in other words, variational autoencoders in which you pre-multiply the KL term with a number beta, and independent of the size of the latent state and independent of the network architecture, the envelope of all of the resulting rate distortion functions that you learn like this are going to give, you know, are going to give you an upper bound on the rate distortion function. If, again, you do what I said before, namely, if your distortion metric corresponds to the negative log likelihood of your decoder model. So you can actually derive that using the information data processing inequality. I'm not going to go through details here. And the interesting thing is that there's also a lower bound. And this is actually much harder. So actually, we looked into old information theory papers. We found a formulation of the rate distortion function by a maximization function over function spaces that satisfy a certain nasty constraint. And now the idea is if you maximize over all possible functions and you restrict your function space to a subset, you get a lower bound, right? Because the maximum is no longer achievable. So what we do is we parameterize these functions by neural networks and optimize them. And because this is only a subset of the space of all possible functions, we get a lower bound of the rate distortion function. So now what we could do with this is as follows. We can now try to estimate the rate distortion functions for various data sets and compare that with how existing compression algorithms, how close they already are to this object. So one data set we looked at is this particle physics data set, which involved sort of coming from an earlier project where we looked at collisions between particles. So there are two particles colliding, two four momenta coming in, two four momenta coming out. So that's a 16-dimensional data set. And there are all sorts of, as you can imagine, non-trivial correlations between these different dimensions. So you might wonder, how well can we compress this data set? And then what we did is we derived these upper and lower bounds. And the shaded region in between, this is where we expect the rate distortion function. Now, is this a trivial result or not? Well, it would be a trivial result if we would find a practical codec that already achieves the upper bound. Because any practical codec naturally is an upper bound. You have practically demonstrated that you can compress your data set at that rate of distortion. So we kind of picked a relatively recent model, and we see that there's still a sizable gap. So in other words, the upper bound is not a trivial bound. You can also look at GAN-generated images and do the same thing. I'm going to skip about that for the sake of time. And now you can actually plot these results into the curves that we saw before. Remember, before we talked about like the rate distortion function being upper bounded by existing codecs, right? But now we look at quality and rate. So now we're actually expecting an upper bound somewhere here. So don't be surprised by that. Just mentally flip everything in your brain. So the information rate distortion function should be somewhere here. And what we showed basically using the architectures we tested is that there's a gap of at least one PSNR that should be harvestable, that should be achievable if we just do a little bit better of codec design. And of course, it could be that we're still underestimating that bound dramatically because we only tested one particular network architecture. Now, you might also wonder, what about the other bound? And now the unfortunate news is that this is actually a really hard problem. So we were successful in sort of a couple of dimensions, up to 100 dimensions, but it turns out that the other direction is just intrinsically difficult to optimize because there's a lot of noise. There are actually results that show that lower bounds to the mutual information are always hard. So the unfortunate news is that this is still sort of an open problem. Okay. Let's get back to climate science. When did I start? At 3:30?
32, 33.
33. Okay, good, perfect. Let's get back to our climate science problem. As a reminder, the original problem was we have these 9 different simulation data sets, and we want to essentially intercompare these different simulations, and we want to basically use compression-related ideas to do that, right? We want to do something related to KL divergences, because KL divergences are measuring distributional distances, and they have this interesting compression connection. Okay. So the first thing we did here was the following. We took a variational autoencoder, we trained it on these kind of simulation data, and learned a latent space. And the first thing to do that, what we did then was to essentially test whether this variational autoencoder was actually able to learn any meaningful representations of the data. So what we did is then we took data that satisfied different criteria and embedded this into the latent space and then visualized the latent space. For example, we observed that if we take data and separate it by data coming from the ocean and data coming from the land, it's actually going to be embedded into slightly different regions in this latent space. So this is actually what you see here. Also, if you color the data by the types of convection, turns out that there are different types of convection that we know about. You also embed them in different regions of your latent space, right? So your latent space definitely has like some semantic structure. So this is good news. But ultimately, we're interested in measuring distributional differences, distribution shifts between the data. And it turns out that you cannot easily compute KL divergences in continuous spaces. What you can do is you can always compute KL divergences in discrete spaces, right? So in other words, what we need to do is we need to quantize our data. Now, how do we quantize our data? There are many different ways. I talked earlier about this idea of transform coding. This time, we're using a different idea called vector quantization. Now, vector quantization is an alternative. It's less scalable, but it has other nice theoretical properties. In this case, it was just perfectly fine for our purposes. The main idea of vector quantization sounds very fancy, but it's really simple. You just take your data set, shown here in this banana shape, and then you just run k-means clustering with a lot of clusters, as many as you can afford. And then those clusters will essentially claim certain areas of your data space, right? And then what you do is you coarse grain that distribution just by looking at the percentages of, what percentage of your data set is being assigned to each cluster. Those are now these kind of cluster probabilities pi k that all sum up to 1. And this is now your coarse graining of your data distribution. And this is exactly what vector quantization does. Now, it turns out that vector quantization has a nice theoretical property, namely if you have 2 continuous distributions, PA and PB, and you quantize them, it turns out that the KL between the quantized distributions will always be smaller than the KL between the continuous distributions. And it turns out actually that the continuous distribution can be defined, the KL between the continuous distributions can be defined as the supremum over all possible quantizations. So in other words, when we work with vector quantization at a given value of k, we always get a lower bound to this true KL divergence between the distributions. And the larger we get in terms of k, the better our results should be. So it turns out that we can do this, right? Turns out here, when we increase the cluster number and we look at KL divergences and forget about now what these different curves here mean, those are the different simulation data sets, you see that these curves are basically separating, right? And so they separate actually fairly quickly already at k equals 40 or 50. So, so we take that as a sign that probably we can work with about 40 to 50 clusters. Yeah.
What's the dimension of latent space?
The dimension of the latent space in this case is 1,000. Yeah. Right. Okay. So this was ingredient number 1. Ingredient number 2 was clustering in the raw pixel space doesn't make a lot of sense. It's too high dimensional. So we need a tool for dimensionality reduction. And to this end, we use our VAE. In other words, we feed data into our VAE. Here are the embedded data. Now we perform this vector quantization or clustering in the latent space, right? For example, with k equals to 3. And then we coarse grain our data distributions by these cluster proportions or cluster sizes. Okay. All right. Now with these tools, we can now finally get sort of an estimate of the KL divergence between the distribution that these different climate simulators produce. We're expecting a similarity matrix of dimension 9 by 9 because we have 9 different models. And what this basically tells us is that if the entries are small, then the models are very similar. If the entries are, if they're white, those are small, those are very similar models. If the entries are dark red, then they're very dissimilar according to this criteria. And what we observe is that there's sort of essentially a majority of models that have like this white spot in the middle that are all intrinsically very similar to each other. And there seem to be 3 models that have like more discrepancies among each other, but also with respect to this sort of majority cluster. So the result here is that seems to be like 6 out of 9 of these 9 models seem to be sort of coherent, and 3 are in some sense outlier models, but we have no statement to tell, you know, which is the correct model. We can only say something about similarities across models. Now, how do we validate this machinery? Well, first of all, we should make sure that our vector quantization method really converged. So we apply, k-means clustering with larger and larger numbers of clusters, and you see sort of visually that these results seem to converge. And now you can argue, did we really need the VAE, or would we have obtained similar results already with PCA or clustering in raw pixel space? And the answer is, of course, no. Well, clustering in pixel space gives you kind of very erratic results. And also PCA is not sufficient, right? So you really need like a good latent representation to converge at relatively low values of k. Okay. Another insight is that actually k equals to 3 looks pretty good, right? It's not too much different from the larger values of k. And in particular, our climate science collaborators were pretty excited about that because with k equals to 3, they could potentially even interpret these different clusters that they found, right? So let's spend the remaining part of this talk about interpretability of these clusters. Now, first of all, how do we identify the meaning of these clusters physically? Just as a reminder, we took these encoded model data in our latent space. We did k equals 3, k means clustering. And now we look at these cluster proportions. The first thing you can do is you can now you can sort of divide up the data according to the locations where the data came from. And so for every location on the globe, you basically plot the intensity of the most frequent of these 3 different clusters. So how frequent do these clusters occur in different parts of the Earth? And so then you get 3 results. What you see here already is that 1 cluster seems to dominate over land and 2 clusters seem to dominate over the ocean. If you now combine this with the vertical velocity profile, so those are these aforementioned wind velocities, but now averaged over space, so we get sort of a vertical distribution. You see that there are 2 top-heavy clusters, 1 and 2. In particular, 2 is very top-heavy, and then there's 2 is top-heavy, 1 is supposed to be a little bit more bottom-heavy. And if you combine these different criteria, we sort of gave these 3 different clusters different names and identified the first one as continental convection, deep convection, and shallow convection. And of course, the climate scientists here in the room can tell more about it. But I mean, one nice aspect that you clearly just see here at the deep convection cluster is that it reflects this tropical band where a lot of moisture is being transported and carried. And this is pretty much where you kind of expect this deep convection phenomenon. Okay. Yeah, let me skip that. Last thing we did, I realized I'm relatively fast, but maybe that's not a bad thing. Then it's more time for discussion. One thing we did was to look at global warming as another distribution shift, right? Not only did we quantify differences between climate models, but we also looked at global warming. And one thing to analyze global warming is to look at, well, if I take a simulator, I simulate weather at present temperatures. This is one data set. Now I take the same simulator, simulate weather at 4 degrees Kelvin global warming. I get a different data set. And now I kind of do this distributional comparison between those two different data sets. And in particular, I look at the differences in these 3 different proportions, right? How much does cluster 1 change? How much does cluster 2 change? And how much does cluster 3 change? And then you get these 3 different patterns. Now, this is a little bit overwhelming. So let's focus only on the second cluster, this deep convection cluster. And what you see here is that this cluster seems to intensify. In other words, it seems to grow after global warming along this tropical band, right? And it seems to shrink in other regions. So this actually means that, like, in some sense, our deep convection overall increases as global temperatures rise, and this is also something that you would expect. Another way of looking at it is if you look at at these vertical velocity fields that are now averaged over space. The solid lines are before global warming, the dashed lines are after global warming. And if you look at the deep convection, so the top-heavy cluster, you see that the overall intensity grows to even higher altitudes. And this is, again, as you know better than I, a sign of global warming. Namely, after global warming, there's essentially more energy in the atmosphere, so sort of convection happens at even higher altitudes. And of course, this is also associated with extreme precipitation and events as such. Okay, so it was a little faster than expected, or maybe that's good. So let me sum up, and then maybe you can chat about it. To conclude, there's been a lot of activity in generative models, but less so in science than in other fields that are more technologically relevant. And at the same time, there's this interesting field of neural data compression, which might potentially revolutionize of how we compress data moving on into the future, although there are lots of problems associated with that I didn't really have time to talk about. Now, the goal of compression is to learn neural compression is to learn compression schemes in an end-to-end fashion. Could be very interesting for scientific data, for example, right? This is something I'd love to kind of chat more with this audience about. We also talked about the connections between variational autoencoders and end-to-end learn compression schemes, and that sort of, in some sense, when you derive learn compression methods from first principles, you will always end up with a type of variational autoencoder. We also talked about sandwich bounding the rate distortion function using similar methods. I also talked about climate science applications, where we talked about model intercomparisons as distribution shift assessments, where we work with a combination of vector quantization with variational autoencoders. And for k equals to 3 clustering, we got interpretable signatures of global warming. Compression has actually a lot of things to offer. It can make information processing more efficient. It can bring in new ideas into machine learning and in information theory. And yeah, that's all I have for today. Thank you so much for your attention. And yeah, thanks.
Thanks, Stephan. Great talk. Any questions? Yeah, starting with early curiosity on this idea.
Yeah, very great presentation, and I'm so excited to see your results. I have some simple questions. So I wonder, what are the what is dimensionality of the input data within the VAE and the latent space? Because when you visualize it, it seems to be 2-dimensional.
Yeah.
And you then choose 3 clusters.
Yeah,
Just
right.
want to know more details.
Yeah, that's a good question. I'm trying to remember the details. I think the original data were 30 vertical levels and about 100 spatial dimensions. So that's 3,000, right? And so we only went down from 3,000 to 1,000, right? So it's not a huge compression, essentially. And the reason is that for this simple architecture, Otherwise, we couldn't easily faithfully reconstruct our data because it's very hard to find a semantic representation of these climate data sets. It's very hard to reconstruct the data unless you preserve a lot of details in your latent space.
Yeah, the second question is you only use one variable, which is vertical velocity here, right?
Yeah.
So I'm just interested to ask, like if you put more variables, and
we get better results.
I'm just curious to see,
Yeah, totally. A lot of things here are sort of for historical reasons, right? I mean, there's one very strong PhD student, Griffin Morris, who did all the work. And for some reason, we started looking at vertical velocities in some sense because it's apparently a relatively, not the simplest type of information from which you can extract all of this. We had an undergraduate student who actually looked at multiple channels. The results weren't fundamentally different, at least in this analysis. But I agree that in general, we should look at multiple channels.
Okay. One last comment. I'm surprised to see the model SAM is so different from the other models.
Icon is also sort of like outliers.
Yeah, I mean, so I'm absolutely not an expert on this, but my understanding is that the SAM model has a certain characteristic. It's like as you know very well, much better than I do, it has like two scales, right? You simulate the weather on a coarse grid, but then you have the feedback with the subgrid dynamics, which is simulated as a one-dimensional system. So I think there are lots of very ad hoc approximations built in there. So I was told that apparently there's no reason to trust very much in this model, but I don't know if you have other opinions on that.
Thanks so much. I really enjoyed your talk. So I was wondering if you try to pass observation among your data set, like either after training to see like observation is clustered with like similar to which of the model that you used, or you include it within the training set.
Observation, you mean not simulated data, but actually
like reanalysis,
real data. Yeah, great comment. Probably, we haven't done it yet. I don't know what to expect there, but yeah. I mean, there are many ways of how you can augment or combine sort of simulations with observations and get better results. Yeah, it's true. Yeah. So at least you could decide maybe which models is correct and which one isn't.
Yeah, thank you for a great talk. So my question is regarding end-to-end sort of latent space modeling. So with free energy minimizing latent space modeling, the definition of the prior is super important for to minimize the reconstruction loss, right? So how would you approach the definition of prior, like besides Gaussian, priors, like what kind of approaches are there?
Yeah, totally. So yeah, priors are indeed very important, in particular for compression. They're like a huge important ingredient in this whole pipeline. It turns out in all these best performing neural compression approaches, you don't actually have a simple prior like a Gaussian prior, but the prior itself is a VAD. Right? So basically you have a two-level hierarchical variational autoencoder. And the reason is that you need a very good entropy model, a good density model in your latent space such that you can really losslessly compress your latent variables more efficiently. So yeah, there's a lot of, but basically nothing changes in the way you train these VAEs, right? I mean, by introducing additional latent variables, you can learn very expressive distributions over lower level latent variables. In the climate science project, we worked with relatively simplistic models. We also looked at three-level VAEs. We got much better results, but again, for historical reasons, the student wanted to wrap up and we didn't really include those latest results into this approach. But yeah, I'm sure you can do much better than what we did if you really care about precision. Yeah.
Yeah, there are questions. Maybe online. Yeah. Wait.
Hi, thank you for your presentation. I just had a small doubt in the vertical velocity profile. Like can you please go to that slide?
The one after global warming?
Yep. So why is it shifting to the left before and at a particular elevation it like moves to the right? The dotted line.
Yeah, why is it shifting to the left?
Like lower.
I don't really know. I could imagine that if it's no, I really don't know. Sorry. Yeah, no, I mean, the only thing really observed is that this, again, the steep convection cluster seems to shift up. I mean, you could argue maybe all of them are shifting up slightly, right, due to global warming, but I mean, this one is really pronounced.
I see. Because in the beginning, at a particular latitude, it like moves to the right, like.
This one?
Yeah, as we go above in the atmosphere, the dotted line leaves, like it goes above in the before global warming scenario.
Okay. I don't know.
Thank you so much.
I should also say everything here is to be taken with a grain of salt, right? I mean, our definitions of deep convection and so on are a little fluid, right? I mean, we actually did some stability tests. We rerun k-means clustering with k equals 3 multiple times. Apparently, the results were always similar. I should say this is kind of really a proof of concept that you can actually learn quite a bit about global warming and climate science effects by not knowing anything about domain science. So that was probably like the main idea, to see how far can we go in a completely unsupervised fashion to understand what's going on across models and what's going on with global warming.
Gotcha. Thank you.
Yeah.
Any other questions? Yeah, maybe.
Hey, sorry if you already answered this, but just about the climate modeling part. I realize that VAEs have some connection information theory and so on, but they're also generative models. I didn't catch if you actually generated data using them, and what do you think about that?
Not in this project. No, not really. No, here we are really only looking at density estimation tasks in some sense. Yeah, I mean, there was some idea originally that we could sort of generate low resolution details, but then that didn't end up in this project. Yeah.
Just quick follow-up then, like just being kind of naive and forgetting the theory aspects. What if you just used a autoencoder without the KL regular, just a regular?
That's a great comment. Probably it might have worked as well, right? I mean, in the end, we didn't really use the priors or anything in this particular project. I mean, the original reason we looked at the autoencoders were we originally wanted to have, we had a slightly different way of assessing the KL divergences in mind. So we wanted to use the elbow essentially as a density estimator and then look at elbow differences as likelihood ratios. But in the end, it turned out that this vector quantization worked much better. But you're completely right. In principle, we could have probably used simple autoencoders as well. Yeah.
Thanks. I don't know if there are any questions online.
Yes.
That's one. Okay. I don't know. Maybe you can read that on your computer.
Yeah.
Rube, if you can hear us, can you type your question into the chat, please?
Oh yeah, I can type. Can I just ask it, or you can't hear it?
Yeah. In the meantime, yeah. Thanks.
Thanks. Great talk again. I even like the parts that weren't about climate science. But my question is about the climate science part. So you were showing that your method for comparing the models was converging as you increase the number of clusters.
Mm-hmm.
And I just couldn't help but notice that k equals 5 was actually more dissimilar to the larger cluster ones than k equals 3.
Yeah.
Do you think is it like dumb luck that k equals 3 worked out, or does it relate back to the fact that there are these 3 regimes?
Yeah, I think in the plot that I showed, we didn't do a great job at adding error bars to our results, which we should probably always do. I think I should also say that this is still sort of in preprint fashion, so we'll do a more careful analysis. I'm pretty sure that this is sort of just error bars that we haven't explicitly noted. So I wouldn't interpret too much into this, I think. Yeah.
Thanks. Maybe we have to. That's the question.
He's typing his question.
He's typing. Yeah.
Here we go. Okay.
Great.
His question's up. Okay.
I was wondering if it is possible to do the compression for climate data where we try to preserve, maybe in lossless manner, some specific statistical information.
Yeah, that's a great question. Yeah, this is exactly what I would also love to explore more. I mean, you could think about, yeah, in these learned compression models, you can always both do lossless compression or lossy compression. You could try to preserve certain statistics, perhaps 100%, right? I mean, for example, you could think about preserving energy and then compress everything else. I think there could be a lot of research in designing appropriate loss functions that are not just mean squared error, but sort of more physics informed. And I think this opens up a whole new research agenda. So I'm really excited about that, actually. Yeah, that's a great comment.
Interesting. So with that, let's thank Stephan again. Thanks so much.